Today's presentation are going to be done by Wesley Wemery, who is FesAus Treasurer and next year Vice President, as he threw his hat into a ring. Yes?
Afternoon, everybody, and thank you for coming along. As Adrian said, we've got two talks on today, so we're starting a bit early, 12:15. So I'll do the first talk, and then my colleague here, Ralph Opperman, will do the second one. So hopefully we'll finish by about 1:15. Hopefully no one will leave early. So my talk, I'd like to talk to you about something I've been working on for a couple of years. Reservoir petrophysical modelling from seismic impedance volumes. And I'm director of two companies, iRPM, Innovative Reservoir Petrophysical Modelling, and also another company that I've formed with Ralph and another guy, Peter, Resource Technology Network. So what I'm going to talk about now, a table of contents. I'm going to go through a bit of background of what the industry does in this area. Then I'm going to talk about current conditions and the current situation. Then I'm going to talk about the objective, what I've tried to achieve and hope to achieve in my processing, and some action, how I've gone about it. And I'm going to show some examples, two field examples. The first one will be the Petrol field, and calibrated to the Petrol 1A well. Then I'm going to go and show some blind testing against Petrol 4, 5, 6 and 7. I'm going to show you what the petrophysical properties look like in the 3D space, and also in the 4D space, the fourth dimension being time. So as production occurs, how does the seismic impedance change? First example is to big water sand, so it's nice and easy. But people have said, well, you need to prove this in a gas thin-bedded reservoir. So I've looked at Wheatstone field, and I've calibrated in the Wheatstone 3 well. And again, I've gone and blind tested against Wheatstone 1, 2 and 4. So I'll show you what this looks like in the 3D space. Then I'm going to talk about some uncertainty in the predictions and conclusions. So initially, 1980s, hydrocarbon volumes were determined in 3D space using this basic equation: gross rock volume, net to gross thickness, average porosity, average saturation, and an expansion constant. And this needs to be determined from at least one discovery well. So I think we're all pretty familiar with this quick look equation. But this equation should only be used as a quick look, but we often use it too much. This requires the average properties of porosity and saturation, but averages remove the variation of the reservoir quality. The global financial crisis could not have been predicted using averages. Similarly, good reservoir quality will never be predicted using averages. So the current conditions, typically we have 5 to 10 exploration appraisal wells that are typically required, and they cost about $100 million each, and we need to drill these wells before we make a financial investment decision. This takes approximately 5 years and includes conceptual based modelling before development drilling starts. So we drill the development wells, and that's when we start producing. So a lot of time, a lot of money. But the end-of-field hydrocarbon volumes from too many major capital projects are found to be outside the uncertainty range. And most of these are below the low case. So here we have in green the initial range of the hydrocarbon volumes, but in red, at the end of the field life, we actually find out too often that the volumes are lower than the initial low case. 10% of the time it should be below there. Sometimes it's 40% of the time it's below there. We often overestimate our volumes. Petrophysical cutoffs, averaging, overestimate net pay. This is due to cognitive bias and other reasons. But this results in underestimating the permeability. And therefore we require 3 to 5 times scale factor in order for the material balance to match the field production, because the permeability is a logarithmic non-linear nature, so it's very different. Too often, the variation around the average value of the property is modelled without regard to the probability of the precise value. So, to give you an idea what I mean by that is, consider the state of a drunk wandering down on a busy highway. His average position is on the centre line. So the state of the drunk at his average position is alive. So we're all happy. But the average state of the drunk, as you would expect, is actually dead. So that's not what we need. The problem is that we can't determine. We know that our maximum's over here and our minimum's over here, but we don't know when this occurs. Our average is down the middle, and we've got an uncertainty around the average, but we don't know when that occurs. What we need is to predict where this trace goes and the uncertainty around that trace, not the average. So my objective is to increase accuracy and validate the accuracy with blind testing. I don't ever remember any modelling actually blind testing anything with another well. You want to reduce cost and requiring less appraiser wells and processing a lot faster. So my objective is to use science, physics, mathematical relationships rather than conceptual stochastic models based upon averages. So I use a deterministic approach calibrated to at least one exploration or discovery well. Then develop a robust 3D prediction that can be used with old or new seismic. Often I hear people with wireline logs, these are logs back in the 70s and 80s, they're too old, we need new log data. You can still use the old data and often get very similar uncertainty results. Similarly with seismic, you should still be able to get a good result from the old seismic and the new seismic. So the action is to calculate the reservoir petrophysical properties constrained or referenced to the 3D seismic trace or the 3D seismic impedance at the well control. So you calibrate it there. Develop relationships for water, gas, oil and residual hydrocarbon at the calibration well. And typically everyone is familiar with Gassman equations for fluid substitution to do this. Then you blind test the predictions against a new or an existing well. This will validate your model. Even if there's large uncertainty on your prediction, just so long as the prediction comes within that uncertainty, then it is a valid model. Populate in 3D space with predictions based upon the calibrated well and use existing relationships for permeability and saturation in the 3D volume. So, the example, Patrol Field up in the border of Western Australia, Northern Territory, up there shown in the green, and here's the Patrol Field highlighted there. So, one of the wells I used Patrol 1A as a calibration, and there's a similar layout in the next few slides, so I'll go through this one in a bit of detail. You've got your gamma ray over here, so your sands where the gamma ray is low, and your high gamma rays where there's non-reservoir, and you can see the resistivity is dropping in the sands, so this is water filled, and then you've got your density, compressional and shear sonic, all your porosity logs through here. So this first track is what I use, a clay, silt, sand petrophysical model. It can be, that's your basic petrophysics that we always do. So you've got your clay and your silty volume, which is really a measure of the variation in reservoir quality, and your porosity in this area here. So then this next track is where I've developed the relationships based upon the log impedance. So at the log scale still, not yet at the seismic scale. So from this log impedance blue curve, which is simply the product of the density and the compressional sonic, I've developed relationships to predict where the clay and the sand is. And so you can see how it compares to the standard petrophysics. The next step is to put it into the 3D space. So you need to extract the seismic trace from the 3D space at the well control, do your seismic conversion, and hopefully this is going to get close to your log impedance, so I start to call this a seismic impedance. And then you get this third column here. So the seismic trace is just a band-limited reflector, and so you do your seismic conversion and then run the same equations through there, and so I get this petrophysical result from the seismic trace alone. But this is the calibrated well, so it should look very good. You need to validate it and test it against other wells. So the Petrol 4 well is a blind test. So I used the same relationships developed in the 1A well and applied to Petrol 4. So you can see it picks up the shales and picks up the sands. Blind tested again against Petrol 5. You can see it picks up the shales and the sands, and the porosity is not perfect, but it's close. But picks up the sand almost every time. Petrol 5, another blind test. Petrol 6, another blind test. You can see that the prediction goes outside of the log data. And one of the beauties of the seismic is that you don't have bad hole issues like you do with the log data. Blind test, Petrol 7. So, what does this look like in the 3D space? Here we've got our Petrol field, our seismic. On the top left-hand corner we've got our calibration well 1A, and then the 4, 5 and 6 wells that I showed were blind tested. And here's the volume of clay and the volume of sand and the permeability that results from these predictions. So now I've got a little video, and you'll be able to see as we time depth slice going down into the reservoir, you'll see the seismic on the top left, see the obvious reflectors that you see when you go and explore using the seismic. But now I've applied these relationships to get the volume of clay, the volume of sand and the permeability. You can see the two sands coming out that you saw in the petrophysical logs. And the inner sand is of better quality. So you can start not just to identify where the sands exist, but now you can tell the variation in reservoir quality. With averages, you won't ever be able to do that. So what does this look like in 4D? So here we've got a drainage capillary pressure function, which is this first curve. So you've got 100% water here, and you imbibe or you drain into here as the hydrocarbons migrate into the reservoir, and you get some saturation, about 30% water saturation down here. Once the hydrocarbons are in place, then with spontaneous imbibition, the water imbibes into the hydrocarbons as the hydrocarbons are produced, and you follow this second curve coming down to get your residual saturation down here, which in this case is about 70% water saturation. You could go and do a third function, which is forced imbibition, which simulates the enhanced oil recovery, whether that's high pressure water, steam, chemicals, to get out some of the residual hydrocarbons. So I go and apply the saturation into the 3D space that I did in Petrol, and I had this vertical slice going through the field, and here's the wells intersections here. You can see the free water level here. So the acoustic impedance here below the free water level is this interval, and then above the free water level with the hydrocarbons in there will give you this acoustic impedance. But then I go and apply the spontaneous imbibition function, and then I can simulate where the original free water level is and the current free water level is. So you can see that the impedance changes as fluid imbibes into the gas. So then it's simply a difference between what was initially in place and what is produced, the impedance after being produced, and you can find a difference model on the right-hand side where the difference in pink is 0, so you've still got your initial saturation, this area has not been flushed. This pink area down below the free water level hasn't been touched, obviously, but the red area is what has been flushed. So now you can start to identify areas that have been flushed and areas that have been bypassed. So missed oil. So the next example is in Wheatstone. So we're up here in the northwest shelf, and that's where the Wheatstone is. So I've calibrated the same process in Wheatstone 3. So you've got your low gamma rays over here, but in this case you've got high resistivity indicating hydrocarbons, and you've got your density and neutron crossing over largely indicating gas. So this is the standard petrophysics in this first track. The red is simulating the residual hydrocarbons, and the pink is what would be flushed as water imbibes naturally through the reservoir. Then in this column is the log impedance. So I've gone and used my relationships from the log impedance to predict the same petrophysical result. So it still picks up where the sands are. Then I go and extract in this third column the seismic trace at that well control. But this particular one is sampled every 2 metres. So it picks up where the hydrocarbons are, but the resolution isn't quite as good. So then I go and do the same seismic trace, except I now sample it every half a metre on the right-hand side. And I start to get much closer to the calibrated well, Wheatstone 3. So I've developed these relationships in Wheatstone 3. They're very similar every time I do it. And then I go and blind test against some other wells. So here's Wheatstone 1. So here's the standard petrophysics again, what I call the log impedance petrophysics, and then again at the 2 metre and half a metre sampling from the seismic trace. These seismic traces are extracted from the well at Wheatstone 1. That's the only thing that's being used in the seismic prediction. Then I just go and apply the relationships that I've developed against the calibration well as I did before, and you can see starting to pick up all these gas sands through here. So blind test against Wheatstone 2. Now this is the notorious Brigadier thin-bedded reservoir through here, and then the Mungaroo below here, and there's a gas water contact right down there. So this is highly thin-bedded. So this is the log impedance prediction. So the relationships are matching very, very well. And then I extract a seismic trace at the well control again at 2 metres. And then I go and do it at 0.5 metres. So I can still get very similar results to what we already know at the log data. Again, blind test against Wheatstone 4, exactly the same results. The resolution at 2 metres isn't sufficient, but you can still pick up where all the gas sands are at half a metre sampling. So what does this look like in the 3D space? So you've got your Wheatstone wells here, and you can see the seismic reflectors showing on the top left. And on the right hand side you've got the 3D volume of clay, and hot colours are high values, and the cool colours in the middle here is basically where the sands are. And you've got your porosity, high colours are high porosity, so your porosity is in this area. And then you've got your permeability. So the permeability I've shaded according to yellow being sand and pink being non-reservoir and blue somewhere in between. So as you go through this, you can see that Wheatstone is coming through here. Now these wells over here are the nearby Iago field. Now a question to the audience, we can see something over here. Can anyone tell me? We've got Wheatstone and Iago. Can anyone tell me what this little field is over here? There's a quick guess. Very good, Jerry. So we've got Wheatstone 3 calibrated in this seismic. We can predict 2 other fields, although this isn't actually the entire Pluto field because the seismic doesn't cover all the Pluto field. The Pluto wells actually sit back over here somewhere. but we can start to predict and see which fields are in communication, because we get a consistent prediction of sand, and we know our pressures, we can see what's communicating. So what are the ultimate recoverable volumes? If we know our in-place volumes with our height function and our imbibition height function determining our residual, ultimately, what is our ultimate recoverable volumes? So one colleague, when I explained what I was doing, he sarcastically said, "Oh, while you're doing the holy grail of petrophysics, why don't you go and do your normal job and just look at the logs?" Well, sometimes I wonder if this is the holy grail of petrophysics, you know. But some models that I've seen recently, you know, they have 15 wells, and they blind test by removing half of one of those wells. And then it doesn't work, so they put it back in there. And I think, it just invalidated your model. I thought that's as bad as it can get. I've seen other models where they've had 13 wells with a conceptual, statistical, neural network modelling, but no blind testing. Because the 13 wells are pseudo wells. They were artificially created in order to build the static model. So the uncertainty. So I'll talk about the log porosity uncertainty against the seismic uncertainty, the final result. So this is the Wheatstone 1 well, and you can see the log porosity on the x-axis varying between 0 and 40%, and the seismic porosity varying between 0 and 40%. There is uncertainty around it. Now, often people say deterministic predictions don't have uncertainty. They do. And this is the uncertainty. You can see the variation around the 1-to-1 line. It should be close to 1. But even standard petrophysics using density porosity, there is uncertainty around that. But what is the uncertainty? So you subtract one from the other and you get your distribution. And often people assume it's a normal distribution, but more often than not, it's not a normal distribution. So normal is just an assumption. But here's your P10, P90. What are these values? It's about plus or minus 10 porosity units. So anything below the P90 occurs 90% of the time. And the P50 is going to be your best guess. But within the P10, P90, you're always going to have 80% of the time it's going to be within that range. So the volume of clay. So the log volume of clay against the seismic volume of clay. Here's the results from Wheatstone 1 again. So this is a blind test well. It's not the calibrated well. The calibrated well is going to be even tighter. So you've got your high volume of clays up in the top right-hand corner. So what's the uncertainty there? Again, you subtract one from the other. You can see this is a bit skewed. So it's, again, enforces the fact that it's not normally distributed. And so we should never use that. And so the uncertainty there is a little bit skewed. So the low case is minus 30% volume of clay, and the high case, is plus 20% volume of clay. So conclusions. What's missing that I haven't mentioned here? Can anyone quickly tell me what I haven't, one word that I haven't discussed? Cost. Well, it's cheaper. I mentioned that earlier, but there's no geological conceptual modelling here. I know next to nothing about geology, so in this case, I don't need to know that. Why don't major corporations employ the average graduate? Because they know from the marks where the best graduate is and the worst graduate. The only reason we use averages is because we can't predict the best quality and the worst quality. If we can predict the best and worst quality, we don't need averages anymore. So no bad hole corrections required in the seismic, but that's a small advantage. The differences with the current industry standard modelling, significant reduction in appraiser wells with blind testing possible. There's no geological conceptual based modelling, no stochastic predictions, no co-creating of dependent variables or properties. Usually we go and model what the porosity is and then we co-create on top of that what the volume of clay is, depending on whether the porosity is high and therefore we think it's going to be a low clay. If the porosity is low, we think it's going to be a high clay, which is reasonable, but the uncertainty in the porosity compounds on top of the next variable as you do that. So there's no use of averages, no probabilities or spread of the data varying around the average value. There's no facies. The orange volume of silt indicates the variation in reservoir quality. There's no cutoffs because we need to apply cutoffs to get our averages, so there's no cutoffs. Property predictions take 2 to 4 weeks rather than 6 months. The products that are produced, as you saw in the two cases, porosity, clay, permeability, saturation, and this is populated in the 3D space. The uncertainty is around the precise predicted value of the property, not the uncertainty around the average property. 4D seismic prediction using drainage, imbibition, saturation, height functions, therefore possible. So the data requirements, at least one exploration appraisal well, 3 or 4 to give you a bit more confidence. Super combo logs is all that I need. All these standard, cheapest logs that we've been running since the 1960s and 70s. Well location coordinates, directional data, 3D seismic, preferably impedance depth data, but I've done some seismic conversion so I can correct for seismic band limited trace data. Preferably wireline formation testers to determine where the fluid levels are, preferably routine core, preferably special core analysis, but I have defaults that are pretty close to what it is, but to make it more accurate, these can calibrate the results. FMI, NMR, tensor resistivity, all these expensive tools are not required to do this. The uncertainty, accuracy of the seismic band limited trace matched to the impedance values. That's where I find the greatest uncertainty, is the seismic conversion. Seismic quality, high frequency, loss, constructive, destructive interference. This is really outside of my realm. This is part of the seismic conversion. I've done my own seismic version, as I've said. Geophysicists know this far better than what I do, and I would trust their inversion, but I would also blind test it against wells. Seismic to log resolution matching, I've shown you how I'm able to come around, overcome some of those problems. The other uncertainty is the two-way time to depth, log depth match. So the references, my two go-to references that I've been using for 20 years are this very first one. We've got Mr. Hugh Crocker here sitting at the front table here. He wrote this paper back in 1980, and this is the first introduction I had to the silty shallow sand petrophysical model. And this model is the only one that I know of that captures the variation in reservoir quality, not just porosity, not just clay and all the others, but the variation in reservoir quality. And then the second reference there is from a gentleman I worked with in Petronas in about 2000, Chu Fok Chu, and he showed me the value of this model. In a few cases, I just sat back and I thought, I'm never going to lose this. So his paper was written 30 years later, but it's still just as valid, and I recommend you read those. Third reference, Sam Savage, a couple of years ago, Chevron colleague introduced me to this book, and this is where I got the drunk walking down the freeway showing you why we don't believe in averages. And all these other geophysical relationships that I read through to develop some of these relationships. That's my talk, and I think we should have Ralph up here next before we ask any questions, unless there's anything burning.
Just a quick one.
Yep.
Gas and water are nicely contrasted in the seismic space, but not so much oil. So I noticed you didn't use any oil examples. Oil fields.
I haven't gotten around to looking at oil, but yes.
So do you think it's going to fall apart, the technique?
No. The acoustic impedance of water and oil is very similar. the vast difference is where you have the gas-band substitution between water and gas. So what I do is I determine where the hydrocarbon column is from the existing well, then I go and apply relationships on that seismic area based on gas field and my height function to go and predict what the water field porosity is in the results, and then I go and put it back in with a height function. So I could do exactly the same with oil.
When you get that 3D model you showed, I think if you had an oil field, it would just look like noise.
Well, both of those examples showed porosity, and it's really, is the sand there or isn't the sand there? And the oil only occurs in the sand, so it would still have the same contrast that you would see, I would think. All right. Mark?
Just one, on the uncertain slide, is the log data smooth to the resolution of the seismic?
The log data is every half a foot, and the seismic data is every half a metre. I think I exported everything into half a metre sampling, so I could display them 1 to 1. So I guess the log data has been scaled up to half a metre in order to display that. Yeah. Okay. Ralph, you want to come up and do your talk now? Thanks for listening. Any more questions later? I'm sure we're both available.